Good morning. My name is Chris Hallum from UE Systems, the UK and Ireland manager. And today we're going to cover a brief overview of the use of airborne and structure-borne ultrasound as part of a predictive maintenance program. So, make sure my slides are working. So today, my name is Christopher Hallum, and my contact details are as below, as you can see. A little bit of background about myself before we go into the actual presentation. My background is as an electrical engineer. I spent over 13 years in the Royal Air Force, doing lots of different types of electrical engineering, from radar systems to communications and satellites. Also qualified as a trainer within the service. When I came out of the service, I went into the rail sector doing some training for the future engineers. I then came to UE Systems as a European trainer and gained Certified Maintenance and Reliability Professional status, which helped me then with understanding the best uses of predictive technologies and in all the sectors. So UE Systems as a company was founded back in 1973. We're a company basically focused on research and development of ultrasonic test equipment. Not a service provider, purely a manufacturer of the equipment, along with license-free software to enable users on their sites to be self-sufficient. From America, we branched out into every continent with regional headquarters in North and South America, Asia, Europe, India, and the Middle East. Myself, part of the European team, where our main headquarters is in the Netherlands, and we have regional representation then directly in Germany, France, Poland, Italy, Spain, the UK, and Ireland. And also in our headquarters in the Netherlands, we also have our calibration workshop. So, first things first, when we talk about predictive maintenance, the first thing also is to talk about really is, do we have a plan on our site? Do we know what we want to achieve? What are our aims and goals? And when we go on to that, we need to think about our assets first of all. And have we done a criticality study of our assets to understand where our bad actors are, where are our pinch points, things that are going to cause us pain on site? We also need to look at what we're currently doing as well. A lot of industries will focus primarily on time-based maintenance, preventative maintenance, but also you need to think about what sort of percentage of my time are we going to use predictive technologies for? Are we going to employ run-to-failure strategies on certain assets because that is acceptable in some areas on some assets? We also need to think about our people on site. And one of the biggest challenges to any site that's trying to introduce a predictive maintenance strategy is the culture behind what people are doing on site. And if we can then also focus on training and development of our people to help them gain new skills, to help us make more improvements on our site. So as part of that plan as well, we need to understand what sort of technologies are best used and best suited in what areas. Now, there are many technologies within the predictive maintenance environment that can help us with doing these things. And if used in combination, can provide a very strong predictive maintenance program to help us identify our potential failures or our potential problems and rectify them as soon as possible without having any impact on production, for example. So, let's actually talk about ultrasound and where that fits in as a predictive technology. So we're going to cover a few of the basics first of all. So the principles behind ultrasound. So as humans, we can hear in the frequency range of 20 hertz to 20 kilohertz. That's the audible range of sound from the age of about 8 years old, when our hearing is mature. From the age of about 8, our hearing starts to degrade and we start losing the higher frequencies. So most grown adults with a good level of hearing will be able to hear between 20 hertz and 16.5 kilohertz. So there are other sounds that are actually in the spectrum that we span out here as well. We have the below 20 hertz region, the infrasonic range, and we also have the ultrasonic range, which is 20 kilohertz and above, so outside of our human hearing range. And this is where the device that we would use sits. So what are the differences between high frequency ultrasound and low frequency audible sound? So if we think about low frequency audible sound, it's very strong and powerful from its source. And when it transmits from its source, it transmits in every direction. It penetrates solid objects, which means locating the source of the sound can be quite tricky because it could have gone through multiple mediums to actually get to us. So it's not so easy to identify where a sound's coming from if it's traveling in every direction. When we get to high frequency sounds, the wavelength of the sine wave of the sound becomes shorter and it's weaker, which means that it's more directional from its source, and it cannot penetrate solid objects. It will become trapped within the object and will not pass through. So this will help us with identifying the source of the sound if we're using an ultrasonic device. As we point towards the source of the sound, we will hear it stronger. As we move away from the sound, we will lose it. So it helps us with pinpointing where it's coming from. There are two ways that ultrasound is generated. The first way is through turbulent flow. So if we think about a pressurized system with a leak, we would gain turbulence from that, and that would generate ultrasound. And in some cases, if it's strong enough, it will generate audible sound. Another way ultrasound is generated is through friction. Anything that's moving, rotating, rubbing together will also generate ultrasound, but that will be trapped within a solid structure. So we would use a contact approach to listen to the sound inside the asset. So let's have a little look at the applications where we can use ultrasound for. I'll cover these now briefly and then we'll go into more detail with them afterwards. The first one being electrical inspection. Using ultrasound to detect valve leakage for valve inspection. We can also use it for bearing inspection and ultrasonic lubrication. We can use it for steam trap inspections as well to understand the condition of the steam trap. And also, one of the bigger uses, using it for leak detection. Now, these applications can be kind of categorized into two main areas. The first being energy saving, and the second being condition monitoring, so checking the condition of our assets. So let's go into leak detection and look at where we can use it, and how we use it, and why. So there are four main reasons behind using ultrasound to help us track down leaks that can benefit our plant. The first one being safety. If we think about compressed gases, it's a pressurized system just wanting to normalize the pressure with the outside environment. It's like a bomb waiting to go off. That's very fragile structures. Also thinking about certain dangerous gases that we don't want to have a leakage that could cause fires, for example, or safety to our employees. The second reason is also economics. So compressed air, compressed gases are extremely expensive. So if we can identify these leaks and repair them, we can make a savings to our company. A third aspect to this is also the environmental impact of that. So if we have horrible gases that are leaking, not great for the environment, but if we have compressed air leaks, for example, we're then putting more pressure on our compressor system to keep our line pressure as high as possible, using more energy in the process, burning more energy and causing more to our environment. And also about quality assurance. A lot of our compressed air systems will actually have an impact on our production facilities. And if we don't have the correct pressure, we could have an impact on our production. So it's also about quality too. So going on to energy savings with leak inspection, a large percentage of our energy wastage can be through compressed air systems. Repairing the leaks can vastly reduce our compressor running hours That's one of the important things behind this. And we also have the potential, if we have a lower level of leakage within our site, we might have the potential to be actually able to reduce the line pressure of our system, which in turn is going to have another effect on our energy audits as well. We can use the ultrasound in noisy environments to detect our leaks. Most plants will be noisy. Again, that's audible sound. So again, we're listening for the ultrasound, the directional sound. And ultrasound, it heightens our senses. It helps us understand. So an air leak in the ultrasonic spectrum will sound like an air leak audibly to you. Okay, so we can pinpoint these areas very quickly, very easily. And with the ultrasound technology, we can identify the leaks, we can pinpoint the location, and we can quantify them using reporting formats, either with the software that comes included with the equipment or via leak apps. And a quick example here of a short leak report that was conducted as part of a demonstration on a site. This took about half an hour, I would say, when we did this little 5-10 leaks in one area. And again, as long as we understand how much a site is paying per kilowatt hour for the energy, we understand the running hours of the compressor systems, and we identify what the pressure is at that point of the leak, then we can actually quantify that. So then we can show what potential savings we can have per year on repairing those leaks. And along with the main format of the actual leak report, the itemized billing, we see the cost of the actual air leak, the size of the leak, and also the energy avoidance and the greenhouse emissions caused by the excess energy usage. And alongside that, we also have then images alongside showing each individual leak and obviously the cost from them too. And again, this report was generated from the UE Systems Leak Survey app, free to download on Android and iPhone devices. So I have a quick question coming in, asking about can chillers, HVAC refrigerant gases leaks be captured? So again, it's a pressurized system. On chillers, we have a pressurized system. If we have a leak, we're going to have turbulence, and the answer to that is yes. I've used it on large HVAC systems. I've even been into local cooperative stores and checked refrigeration systems there and identified leaks with ultrasound too. So yes, it is possible. So that's the coverage of leak reporting for now. Next one we go on to, if we're looking at energy savings as well, is also looking at how we could use it for steam trap inspection for energy savings as well. Steam systems are an incredibly inefficient system themselves because of the nature of them. It's something trying to heat up and it's always going to try to cool down. So if we can identify our faulty steam traps, because the aim of the steam trap is to obviously hold back the steam and remove the condensate that's actually causing the cooling down effect of the steam itself. If we can identify a faulty steam trap and get it replaced, then we can improve the efficiency of the actual system itself. So I do get, if I'm having a few problems maybe with the sound, I will try and get that increased a little bit just now. Just check that sound. I will increase it as best as I can, guys, and just bear with me on that. So with the steam trap inspections, obviously using ultrasound technology will allow us to have an immediate assessment of the steam trap operation itself and its efficiencies. An inspector's knowledge also of the subject area will also help with understanding the condition of these traps. There are many, many different types of traps, and understanding how they operate will help us understand how they are working. So is it an on-off trap? Is it a continuous flow trap? Depending on the type of trap will also depend on how it sounds. And again, it's using those senses to help us guide our way through. of steam trap operations in place on sites, and we have our continuous flow and our on-off design. So we have our opening and closing mechanical traps and our continuous flow. So ultrasound will be used for mechanical based traps. Okay, if there is movement in there, we will detect the turbulent flow inside the system. And again, it's turbulence inside the pipework, so the ultrasound is trapped within the structure. So this is where we will actually listen using the contact approach. So, some examples of when they are good, and hopefully these sounds will be not too loud in your speakers. So the first one, for example, is an on-off trap, a thermodynamic dish trap, and it would sound something like this. So you can hear the turbulence increasing as the steam trap opens, and then the ultrasound dropping as it closes again. That indicates to us that a trap is opening and closing correctly. The type of trap and the OEM's guidelines as to how often it should cycle will depend on whether the assessment is good or bad. If we then go on to a continuous flow trap, a floating thermostatic trap, for example, that will deal with higher levels of condensate, we would expect to hear a steady flow of turbulence on this. Now, for example, in this one here, we're going to have a metal ball. It could be a free float or it could be on an armature. Now, we might expect to hear on a free float, for example, the metal ball inside knocking about within the body. So if we hear that, that's fine, but we want to be listening for the turbulence inside as well. So as we can hear from this sound then, we do hear the ball flow knocking around inside the trap. That's because it's floating on a bed of condensate. But also in the background, we can hear the steady flow of turbulence, which tells me that this trap is good. So when a trap does fail, one of the most common ways it fails is in the open position. So that means that if it's failed in an open position, we've got a continuous flow of steam at high pressure, which means we would have or expect to hear a large amount of turbulence. So when they're not so good, it would sound something like this. As you can hear from that sound, it is just straight through turbulence. There is no fluctuations in the sound. Okay, and just as an example there of a thermal image showing a steam trap that is blowing through that has high temperature on the outlet to the inlet. And that's what brings me on to talking about having a two technology approach sometimes can also help us with understanding the condition. Because one technology will be able to hear the problem, and the other technology will be able to see the problem. So for example, on a good steam trap, we would expect to see a higher temperature on the inlet of the trap and a lower temperature on the outlet because the condensate is going to be cooler than the steam on the other side. But that doesn't tell me that the trap is not working correctly because it could be the fact that the trap is blocked. So this is where using ultrasound then will also help us with understanding the condition. And if we have the ability to do a sound recording, then we can see that on spectral analysis of the sound increasing and decreasing. Again, evidence is key when you need to justify if you want to do something on site. So, a short case study. Okay, there's a short case study here from a training that I did some time ago where we looked at a few traps. And in this case study, this is a thermodynamic dish trap. Now, what we would expect to hear when listening to a thermodynamic dish trap would be opening and closing, so an increase and then decrease of turbulence every 2 to 10 times per minute. So that would then indicate to us a good trap. And we did a sound recording on this one, and this is what it sounded like. So what we can see here from the sound recording is 2 increases in turbulence, and we can hear the clear opening and closing of the steam trap, which indicates to me a good steam trap. This is a good example of a trap. Now, on this site, there were lots of these traps, so we were able to go around and compare them to this good sound recording to understand the condition. So we came across another one, and we took another sound recording to do an inspection, and this is what we came across. So from this sound recording, we can see very clearly lots more turbulent flows. So we can see more, the trap opening and closing more and more each time. So this is telling me that the trap is working, but it's now losing its efficiency. Okay, so we can see that now this trap is removing condensate, but maybe not as efficiently as it should be. So this is an indication of a steam trap that is not working as good as it should be and could be on its way out. So we would maybe monitor this a bit more closely and take more readings to make sure that we can keep it good. Now, I'm still getting a few questions about the audio quality, so I'm just going to try something different again and see if we can get a better quality of that sound. I'm hoping now that this will be a bit better for you. Hopefully it will work. You'll have to bear with me, I'm afraid. So, right, I will carry on. I'm getting some people telling me now that that is better, so I shall continue. So, with steam traps, as you can see, we can identify the condition. We can compare like for like traps. Okay, so as you can see from this one, we see the ideal steam trap, and in the second recording, we can see one now lacking efficiency. And sometimes, especially with thermodynamic dish traps, a common problem, because it's such a harsh movement of the disc inside, it can cause erosion on the actual disc itself. And then that means that it doesn't make a perfect seal. And in that respect, then we'll also hear it chattering away, you could say. So this trap, for example, on the second recording is getting close to that point because it's opening and closing so much. So glad that the sound is working better now. It's always good having these technical issues at times. But again, that's looking at steam trap systems, and we can now move on to our next application. So another very common use for ultrasound is in mechanical inspection. As we were saying earlier about ultrasound generating friction, okay, friction is that generates our ultrasound. If we think about rotating assets, they are continuously generating friction, which is also continuously generating ultrasound. So we can use ultrasound devices for trending, for analysis, and to understand what's going on within our assets as well. So there's always a big discussion about reliability, about will help improve the reliability of your plant. I would like to look at it as a slightly different approach and say that predictive technologies will help improve the availability of your assets on site. So reliability, in my opinion, is built into an asset from the start. Once it's built in place, the reliability is set. With predictive technologies, we're using it to understand the condition to help us prevent a potential failure, hence keeping the availability of the asset there at a much higher rate. If we do detect failures with predictive technologies, and then we use that feedback to help with root cause analysis and feed that back to the designers may be able to change the design of the asset to improve the reliability from the start, or maybe improve the maintainability of the asset. We also need to understand what sort of failure modes are we looking for, because not one technology is going to help us with covering all potential failure modes. So always looking at maybe a 2 technology strategy will help you understand maybe more of the failure modes, or maybe catch something at an earlier stage. And when we talk about the P to F curve, we're always looking at, where can we detect a failure at its earliest case? And universally known, one of the first changes in an asset when there is a potential problem occurring is a change in its ultrasonic emission. So if we're using ultrasound at an early stage with set baselines, we can detect the very smallest of changes at an early stage, and then maybe using other technologies to help us confirm that. Now, we can also use that as a predictive, but also as a proactive approach when we think about lubrication. Again, with lubrication, we're talking about friction. So if we're using the ultrasound device with an asset that is in good health, that requires lubrication, we can use the ultrasound to monitor the friction as the grease is applied to the asset. So for this, we have the friction in the bearing being produced, which is generating the ultrasound. And as we said, the ultrasound doesn't penetrate a solid object. So we use a contact approach, a stethoscope approach, to listen to the ultrasound trapped within the body of the structure. Now, we use the contact approach as a waveguide to pick up the sound from the structure and make a judgment and maybe do a sound recording as well. So if we think about a good bearing that's adequately lubricated, will have generally lower levels of friction generated, and it will emit comparatively low amplitude of ultrasounds. It should be smooth and uniform in nature. If you were to close your eyes and picture what you think the sound would sound like, it would be smooth and uniform because it's all nice smooth parts. If we have a bearing fault or a potential problem occurring, we're going to start seeing an increase in the ultrasonic emissions. But also, we might see a change in the tonal quality. So it's not always just about the level of ultrasound being produced, it's the quality of the ultrasound being produced as well. If we start to hear repetitive impacting sounds, if we're hearing knocking sounds, we might even hear a change in the sound wave up and down as such, maybe indicating some sort of imbalance or misalignment, for example. The characteristics of the sound could change. So as we talk about audible quality, it's always important that we have headphones connected to our ultrasound device and we're listening as we're doing this, because the signature can indicate conditions of the bearing. Like I said, an increase in amplitude as well as a change in the audible quality of the sound can indicate a potential problem. So for example here, I'll play an example sound of a good bearing, which should sound smooth and uniform. So again, smooth, uniform sound. At the early stages, we may get irregular, impacting, popping sounds that might indicate to us an early stage problem. And that would sound like this. As we can hear from that sound there, we're hearing now crackling sounds in there, not very repetitive, but again, indicating a very early stage problem. And then when we get to the extreme damage side, it's very clear audibly from the quality that there's something wrong. once we understand, okay, what we're going to pick up with the ultrasound. There are limitations bearing in terms of the type of bearing. Only ball bearing, other types of bearings can be checked. So again, any type of rotating asset or rotating bearing will generate friction. So we will be able to pick up the ultrasound emission coming from that bearing. So it doesn't matter on the type. Sometimes you see ISO standards when it comes to vibration and the types of frequencies we're picking up. With ultrasound, the principles are the same, but slightly different. So there's different operating conditions. As long as we understand that the bearing is rotating and there is friction, it doesn't matter on the speed, but we will get ultrasound. So the answer to that question is we can check all types of bearings with this. So a quick case study here. This is this was on a demonstration on site a few years ago, where we came across outside a few motors that were driving some pumps. We came across them. My first question was about the lubrication program on site and what lubrication is being done. With this, they told me that they didn't know when it was last lubricated. So I had no record of when the lubrication was last done. So what we could do is the two motors were side by side. They were under the same speed and load and the same type. So we could take comparative readings to get an understanding. So we came to this one. As we can see from the image, it was registering 29 decibels and the sound was pretty smooth. As we can hear from that sound there, it was pretty smooth and uniform. But in my opinion, I believe that if we were to apply some grease to that, that sound would probably reduce in sound. So another couple of questions coming in at the moment. The squeaking sound, what was the squeaking sound? That is the metal on metal sound that we're picking up there, a very severe lack of lubrication, which is causing damage to the bearing. And also things like impeller wear or wear on the rings. Again, if we've got a good baseline and we understand what we're listening for, if we have damage to the impellers or the rings inside, it's going to change the ultrasonic emission. It's not necessarily going to tell us that we have impeller wear or the rings are wearing, but it's going to tell us something has changed and not for the good if we have good baselines. So going on to the case study again. So we checked the first one. We had a good sort of comparison method to actually employ here. So we went to the second motor, and again, looking at predictive technologies, we're using the same point, the same frequency to make sure we get a good comparative reading. We came to this motor, checked it on the same point of the drive end bearing of the motor, and we could see quite clearly that we had a large increase in decibel value. So again, no record of when it was last lubricated, a large increase of 32 decibels, and the tonal quality had severely changed this time around. And this is what it sounded like. As we can see from the screenshot here, from the time series, we can now see a very large increase in amplitude. And also, it no longer looks smooth and uniform in nature. So again, this is indicating that there is something not right with this bearing on this motor, and they should be very similar in amplitude and tonal quality. So again, we can see here that this bearing would show concern to us. We could also employ a comparative method using FFT with ultrasound. So as we can see here, the recording of the first drive end bearing of the motor on the white trace, and then the green trace being the second motor. And we can see the carpet level of the ultrasound being a lot higher, indicating a problem. So a quick question about how important is it using the correct frequency range. The correct frequency range, really looking for bearings, is around 30 kilohertz, as long as we are trending at the same value. So if we are looking at an asset at 30 kilohertz, every time we take a reading, we want to be at the same frequency. Because if you change frequency, then you're going to get a different decibel level in that range. Okay, so this motor, after this demonstration, was taken out of service, and they reported back to me that when they took it out of service, the drive end bearing fell apart in their hands. It was on the verge of failure. So again, another good find on a fortunate demonstration at the time. So moving on to another case study on another site, we were looking here at a reduction gearbox. Now again, we have many rotating parts within a gearbox. We have the input shaft, we have the output shaft, and we also have our mesh in the body as well. And again, ultrasound is directional. So wherever the sound is strongest will be where the source of the sound is coming from. Now again, rotating parts in a good asset will be smooth and uniform. So when we listen to this, it should be smooth and uniform. If we hear anything abnormal, if we move our contact module around the actual asset, we can locate the source of that sound because it will be stronger at its source. So this is what this reduction gearbox on the body sounded like. So we can hear from that it's smooth and uniform. Okay, and that's what we want to hear. So a couple of quick questions again. The software is available license-free for the users of this technology. You can just download it from our website. And the S in the picture is the level of sensitivity on our probe. So we can adjust the sensitivity depending on the amount of sound that we're picking up. So now we know what a good gearbox sounds like, smooth and uniform. We can compare it to other ones of similar design. So the next one we came across had a similar level of decibel value, but this time had a slightly different level of sound. And this is what it sounded like. Oh. So in this sound recording, we can hear quite clear repetitive impacting sounds. We can also hear that squeaking sound, which might indicate a lack of lubrication within inside the actual body of the gearbox. And this sort of sound would indicate to us that there's probably a problem with the mesh or one of the teeth, for example. Now, again, it's not going to tell you exactly what the problem is, but it's already telling us that there is a problem within this. And this is where we might then employ another technology to help us with the actual diagnosis. So with the oil inside the gearbox, there's a quick question coming in again. The oil in the gearbox will dampen the ultrasound. It will dampen it slightly, but you'll still pick up the sound. And again, as we have a reduction, we're going to start hearing those squeaking sounds, which will indicate that for us. Okay. So again, this is another example of how we can use ultrasound to help us with a quick, simple inspection of the actual asset. So going on to slow speed applications, this is an area where ultrasound really does have a good benefit with predictive technologies. Because again, even at slow speed, we're generating friction, so we're generating ultrasound. Okay, so we can actually still diagnose and listen to the condition of our bearings. So at slow speed, we're going to produce less friction, but it will still produce ultrasound at just a lower emission. So this helps us with identifying the condition. And also when it comes to slow speed bearings, seeing a rise in decibel level is not necessarily as important as understanding the tonal quality of the bearing. We need to listen to the quality of the bearing because again, we want to hear smooth and uniform sounds. On a slower speed bearing, when we start to see damage occurring, even at a small level, we will see a change in the tonal quality. So in extreme slow speed bearings, we're talking really slow bearings, the emission might be really, really low, and maybe not quite audible. This sound here, there is sound here, believe it or not, and you may hear it, and I'll just play it now. So that one's just played there. That's extremely low level. You probably would have had to turn your speakers up for that one. But again, we can still hear the sound. It's smooth and uniform in nature. A normal slow speed bearing, so we're talking maybe something between 10 and 30 RPM, for example, will have, again, a smooth and uniform sound. So again, nice and smooth and uniform. Now, when we get to slow speed bearings that have a problem, we're going to hear a very clear change in the sound quality of it. So again, you can hear quite clearly a change in the tonal quality, but that would not necessarily produce a much higher decibel value. So just going on to a case study now, this was one of my favorite case studies that I've ever come across. This was part of a demonstration on site looking at a super dryer, which had 8 bearings that were all resting. The dryer itself was resting on a set of motors, and it was rotating between 7 and 10 RPM, and the bearings were quite loud and quite large. And again, this was only in operation for about 6 months at the time, so relatively new, should be in good condition, and all of the bearings were the same type, were the same speed and load. So we could do a comparison method to actually listen to the bearings and understand what's going on. So as part of the demonstration, we took sound recordings of each of these bearings just to compare them, just to see what they were like. So of the 8 bearings, 7 of them registered 0 decibels on the display, but the sound was still audible in the headphones, which meant we could still do a sound recording for comparison reasons. And this is what they sounded like, the 7. So again, smooth and uniform. So that was what we would want to hear. And to be honest, after 6 months, that's what I would expect to hear. Now, as you can see from the trace on the time series there, over a period of 15 seconds, there was no impacting sounds, nothing standing out, everything good. One of the bearings we came across registered 2 decibels on the display, and we could hear in the headset a very faint ticking sound. Now, as I play this through my laptop, it's now being amplified a bit. So, but this is the sort of sound we picked up. So, as we can compare now, we can quite clearly see repetitive impacting sounds. Now, this was quite astonishing to hear a sound like this after 6 months old in operation. And we had a few people there that would use their good old-fashioned screwdriver to the side of the head, putting their fingers on the actual housing of the bearing, saying, I can't hear anything wrong. I don't think anything's wrong. And we were stressing that there was a problem with this bearing. So they took a sample of grease, and metal particles were identified within the grease itself. So using the ultrasound trace from this and the results from their grease sample, they decided to take some action about a week later. And after that, they sent me some feedback actually and said to me that they did identify a problem. So they sent me some pictures. As we can see from this bearing, there was quite a lot of damage. There was some severe damage to the outer race.
the cage had been damaged, where we can see one of the rolling elements had now moved by 90 degrees. And we could hear quite clearly the repetitive sounds from that bearing. So again, this was a great find because this would have had a severe impact on the site's production. So again, this was 2 decibels in sound. It was not very high decibels, but that's a 200% increase on the actual other readings. So again, a great find and a good use of ultrasound for slow speed bearings. So when we have our critical assets on our sites, we do see a lot more these days issues with access and people not being able to maybe get into, monitor or maintain their assets very well for these sort of predictive approaches. So does that mean we need to stick online systems on there? Not necessarily. It might be a fact that we could look at using remote access sensors where we can wire and fit sensors remotely, running them to a distribution box where we can access and plug in our ultrasound device into the actual probe. That way, helping us with taking our readings on areas where we cannot access and being able to collect data sometimes on a much quicker timescale. So also, there is the need sometimes for online monitoring, depending on how critical the asset is. It's also looking at, do I want to be knowing how soon something's going to fail at the earliest stage, where things like forecast systems that are mounted on, we could actually listen to. So for example, you may have your critical asset wired with remote access sensors run into a forecast system that can be connected on a network. And then with that, it will monitor 24/7 our bearings. We can set alarm levels, we can set baselines, and we can then also get readings sent to us on a periodic basis, just so we know that we're actually getting good sounds and good readings. And then when it does hit alarm levels, we can also have it notify us via email, via the software, or via chat groups even as well. Other online monitoring techniques might be looking at analog sensors as well. A lot of assets will have human machine interfaces on them where we can connect an analog sensor, a 4 to 28 milliamp sensor, via a PLC so we can monitor as well. So I do have a few other questions coming in, guys. I will endeavor to answer them. I know that we're getting close to our 1 hour point at the moment, so I'd like to just get through what we can, and I will make sure I get these questions answered. So when it comes on to lubrication with ultrasound, again, we're looking at the friction levels. And using ultrasound, we can listen as we apply the grease. And it can help us then with understanding when to lubricate as well, because again, we can set baselines and alarm levels that can notify us when there is a rise, and we can help us with actually applying the grease. So when we apply the grease while we're listening, we want to apply grease slowly and consistently, listening for a drop in decibel value. Because if we see a drop in decibel value, that tells us we're reducing the friction within the bearing. As we continue to lubricate and the sound continues to go down, we then understand what the bearing needs. Once the bearing decibel value does not drop any further, that's the bearing telling us that there is no more grease required and it has enough. If the decibel level starts to rise as we grease, that tells us that we are now starting to over lubricate. And that is when we would stop greasing. We need to stop at that point. Because if we hear a sound increase, that is us over lubricating. So we lubricate until the bearing sound does not go any lower. So again, an example of a good bearing that would require lubrication will be just a higher, smooth and uniform sound. And then this sound recording is a sound recording of a bearing being lubricated. So as you can hear from that sound file there, that's where the bearing is having grease applied to it and the sound is reducing until it doesn't reduce any lower, and then we stop greasing. So the main aims of this is to lubricate slowly. We lubricate until the decibel value returns to its baseline or as low as it will possibly go. And if the sound starts to increase, we know that we need to stop because that is indicating an over-greasing of our bearing. So in conclusion to the use of bearing inspections, again, ultrasound is maybe a good technology to first implement if you have no predictive program on site to help us gain quick information on the condition, because again, we're using our senses and it's quite simple to use. And if we use it in conjunction with other technologies like vibration analysis and oil analysis, it will help us improve detection rates of our potential failures. Again, a key area for using ultrasound will be the lubrication and the slow speed applications. There's some great wins that you can see from that there. So going on to one of our last applications is electrical inspections. So again, with this, we can use ultrasound as an efficient method for detecting electrical faults in the early stages. If we have any sort of electrical discharge, it's generating turbulence in the air around it, which in turn generates ultrasound. So the things that we can detect with electrical inspections when it comes to ultrasound are such things like corona, tracking, arcing, and mechanical looseness. Each of these will have their own sound characteristics. And again, because ultrasound is directional, we can pinpoint where these are coming from. So advantages of using ultrasound for electrical inspection are things like it's non-intrusive. We don't have to have eyes on the assets to be able to take readings. We can use the contact approach to listen to what's going on inside the cabinets. We can inspect from safe distances using airborne ultrasound. As I was saying, we can inspect on closed systems. Again, another safe approach to it. And it could be used greatly in combination with thermal imaging. So again, using that two technology approach. So again, one technology would hear the problem and another would see the problem. Again, building up that evidence, okay? That evidence that we need to be able to justify what's actually occurring again. So a quick case study here that was supplied to me by a service provider, a user of the technology. Again, this was a 400 volt buzz bar, a three-phase fuse connect that was fitted into the buzz bar. And again, they used the contact approach to listen to what was going on inside. So we used the contact approach, they took a sound recording and they heard this sound. So again, there's no moving parts within inside this asset here, within this cabinet, so we shouldn't expect to hear any sound. We hear quite strong discharges occurring there, which is an indication to me that there is arcing occurring within that cabinet. So that would mean to me, would I want to open that cabinet with that live? Again, a great indication of doing something safely. So another case study that was given to me by a service provider out there that's a good friend of mine, and they use thermal imaging and ultrasound as part of their standard service inspections in a high-rise building. And what it was they were looking at some high voltage transformers and listening for sounds. They would scan the environment first of all with ultrasound to listen for anything abnormal. If anything was picked up, they would identify the source of that sound, where it was coming from, and then confirm with thermal imaging. And this is the sound that they picked up one day when doing the inspection. So you could hear these crackling sounds that don't sound normal. And again, it was pinpointed then to some cabling where they pulled out then the thermal imaging camera to confirm the source of the sound. Okay. You could then do a visual inspection and see, obviously, the heat buildup marks, identifying that there is a problem there. From the sound recording, I can tell that that is tracking occurring. These users then turned the lights out and took a video recording to see what actually was occurring as well. And hopefully you can see this video. In the middle of the screen, look for the discharge. So as you can see there, it was quite evident that tracking was occurring. But again, there's a lot of sound going on inside the room from the transformer itself as well. So using ultrasound to pinpoint these things was paramount and very useful. Again, using multiple technologies to actually help us with identifying and showing the evidence. So yes, when it comes to electrical inspections, safety is paramount. Obviously, having an inspector that understands electrical principles and understanding the assets should always be the one doing the inspections. Treat electrical systems with respect. And again, using ultrasound, we can use it from a safe distance with our first use checks, but it does not replace thermal imaging. Again, one sees the problem, the other hears the problem. Put together, they work really well hand in hand. Okay, so partial discharge. I have a question about, can we use it to detect partial discharge? Again, partial discharge is producing turbulence, which is producing ultrasound. So we can use ultrasound to pick up partial discharge. And you could argue that partial discharge is also part of looking at arcing and tracking as well. It kind of comes under the similar sort of spectrum as well. So in conclusion then, to the use of this webinar now, I appreciate we're getting to the hour point now. Ultrasound, hopefully you can see, is a very versatile technology. So there's many applications that we can actually use the device for. It's also a very simple technology to operate. Again, we actually use this to heighten our senses and actually understand what's going on. We're picking something up at an earlier stage than we could do audibly. On another side of things, I believe that all plants should be looking to improve their energy savings on site, and leak detection, for example, is one very quick and easy way to make fast gains on your energy savings on site. Also, think about focusing on your functional failures that you experience and deploy the right technology to identify them, because using multiple PDM technologies will help you improve the way you do things on site. Most technologies will work hand in hand. They will help you with that evidence. Secondly, train and educate the workforce. Training is the most important thing when it comes to using these technologies. You cannot expect somebody to have a new technology and understand how to use it straight away. Education is key. And again, the other thing is culture. Make sure that you have that culture on site to want to make improvements, to want to make gains. I would like to thank you all for attending today, for your time. And I see there's some questions coming in. What I'm going to do after this, I'm going to take a copy of all of the questions in this group chat, and I will endeavour to get back to you on them. Please feel free to get in touch with me via email or phone number on here as well. You can also visit our website, where there is a great learning centre that is free to use and free to access, that has lots of case studies and sound files. And we're always happy to help. UE Systems are there to help you get the most out of your equipment on your site. Okay, so thank you for your time today, guys. And like I say, any questions, please feel free to get through to me anytime. Thank you.